Hello students, this video is about one of the most important chapter in 11th CBSE chemistry or first PUC, that is chemical equilibrium. Now, first of all, let us understand the meaning of equilibrium. Here you have one picture of tug of war, and here you can find that both right side and left side you can find same force, and this attains a type of equilibrium, and that is static equilibrium because there is no motion here. Let me tell you one more example for equilibrium. For example, in one room there are 50 persons are staying, which has one entry and one exit. Now if at a time if 10 persons are entering the room, which is already having 50 persons, and 10 persons are leaving the room at a time, 10 persons are getting into the room and 10 persons are getting out from the room at a time. So how many people remains in the room? Yes, 50 will be constant because 10 getting in and 10 getting out. So 50 persons remains in the room. That is one of the example for equilibrium. And we are talking about chemical equilibrium. Students, first of all, you remember most of the chemical reactions are equilibrium. And in chemical equilibrium, you are going to find dynamic equilibrium. Dynamic what? Physical equilibriums are static, chemical equilibriums are dynamic, which means what? Static means no motion, whereas in dynamic you can find constant motion, that is considered as dynamic equilibrium. Let us understand further. Now if I considered there is a reactant called A, which is converting into product B. A is a reactant and B is a product. So A converts to B, a reactant converts to product in a forward reaction. If in the same rate the product B converts to reactant A, then it is considered as equilibrium, which means what? Rate of forward reaction is equal to rate of backward reaction. Conversion of A to B and B to A occurring in the same speed, then it is considered as chemical equilibrium. So a chemical equilibrium occur when the forward reaction and reverse reaction rate is same. Both forward and reverse reaction rate is same, then it is considered as chemical reaction. Here what happens? Reactants react to form product. For example, reactants here in this particular reaction is nitrogen and hydrogen. So 1 mole of hydrogen combines with 3 moles of hydrogen. These are the reactants. They combines to form 2 moles of ammonia. Reactant reacts to form product, and product, again this ammonia product decomposed to give back hydrogen and nitrogen. If both occurring in the same speed, formation of product and formation of reactant back, if it is occurring in the same speed, it indicates what? Chemical equilibrium is dynamic. Why dynamic? There is a constant motion. What motion? Reactants are converting into product is decomposing and give back to reactant. There is a constant motion of reactants and products in both forward and backward reaction. That indicates what? Chemical equilibrium is dynamic. We have an example of Haber's process where nitrogen and hydrogen combines to give ammonia. Now initially, if you see the initial concentration of reactant and product or initial molarity, nitrogen 2.8 moles, hydrogen 4.4 moles, ammonia 0 moles, because reaction is not yet started. But once the reaction is started at a particular temperature of 450 degrees Celsius, we can find the reactant nitrogen and hydrogen combines to form ammonia. And after some time at that particular temperature, we can find that the molarity of nitrogen has been decreased from 2.8 to 2. molarity of hydrogen has been decreased from 4.4 to 2, whereas molarity of ammonia, which is a product, has been increased from 0 to 1.6. So in a chemical reaction, we can find there is a decrease in the concentration of product reactants and increase in the concentration of product. But at one particular time when the reaction attains equilibrium, you cannot find there will be change in the amount. For example, here these particular amounts do not change because new ammonia formation and decomposition of old ammonia is occurring at the same rate. That's why those amounts are not going to change. I hope you understood that. Now let us understand further. Now we must remember that nearly all the chemical reactions are equilibrium reactions. Equilibrium reaction, the rate of forward reaction is equal to rate of backward reaction. In exam they are going to ask why equilibrium is dynamic. You have to explain in terms of forward reaction and reverse reaction. Now for any kind of reaction, for a particular equilibrium reaction, representing equilibrium constant K can be represented as the ratio of concentration of product divided by concentration of reactant raised to power their coefficient. Means rate law or equilibrium expression K can be represented by concentration. See, if you are something representing in the square bracket, it means concentration of product divided by concentration of reactant. If you are finding some stoichiometric coefficients, then that stoichiometric coefficient we have to write in terms of raised to power. For example, for this particular reactions of Haber's process, we can represent the equilibrium constant K as concentration of product, which is the product here in this case ammonia. Ammonia is the product NH3. What is its stoichiometric coefficient? 2 raised to power 2 divided by concentration of reactant. Which are the reactants? Nitrogen and hydrogen. Nitrogen concentration. Stoichiometric coefficient what? 1 you write, you don't write same. Another reactant, which one? Hydrogen H2. What is its coefficient? 3 raised to power 3, that we should mention. So here we have represented the equilibrium constant expression for this particular Haber's process reaction. You can understand there. Now if you want to calculate Kc, numericals are going to be asked like this. So by applying this formula, we can able to find out the Kc value for this particular Haber's process under these values. So Kc is equal to concentration of ammonia, how much? 1.6 raised to power 2, because stoichiometric coefficient of ammonia is 2, divided by concentration of nitrogen, how much? 2, that you have written here, into concentration of hydrogen, how much? 2 raised to power what? 3, that we have represented here. So in this way, if we calculate by applying this formula, we got Kc value is equal to 0.16. And children, please remember, equilibrium constants are unitless. They won't have any unit. Remember this. Then one more another very important point for the entrance exam, you need to remember that if equilibrium constant K is greater than 1, it means what? The reaction is proceeding towards product. Reactants are converting into product. Remember this. When rate constant K is greater than 1. Another possibility is what? If the rate constant K is less than 1, then reaction proceed towards backward, means products decompose to give reactants. Remember this. We have one more example, that is the decomposition of carbon tetrachloride, which is a gas, at 700 Kelvin to solid carbon and 2 moles of chlorine gas. Now for this, if you want to represent the equilibrium constant, then the representation is Kc is equal to concentration of product C into concentration of chlorine raised to power 2, because there is a stoichiometric coefficient, divided by concentration of reactant, that is carbon tetrachloride. So this is a representation. But as this reaction is heterogeneous means what? You can find the reactants and products are in different phases. Of course, there is one product chlorine which is in gaseous state, which is equal to the gaseous state of reactant carbon tetrachloride, but we have one more product, that is carbon, which is in solid state. So if any solid or any non-homogeneous reactant or product will be there, then the value we have to consider as 1. So in that case, here the non-homogeneous product is carbon. That's why in place of the concentration of carbon, we can consider as 1. Then we will get one new formula for this particular reaction, that is Kc is equal to C, concentration of chlorine raised to power 2 divided by concentration of carbon tetrachloride. Here in place of concentration of carbon, we have taken 1 because it is non-homogeneous. I hope you understood this, because in exams they are going to give such type of questions. Then I'll ask you to identify the correct equilibrium expression. So be careful about that. Now we are going to learn the relationship between equilibrium constant Kp and Kc. So children, equilibrium constant Kc is the equilibrium constant in terms of concentration, whereas Kp is the equilibrium concentration in terms of partial pressure. Okay, C concentration, P is pressure, remember this. Now we have to derive a relationship between these two, Kc and Kp. First of all, I already told you, if you are representing anything in the square bracket, it means molar concentration, okay, that you remember. And we know that the Kc is equal to concentration of product divided by concentration of reactant. We have an equation where capital A and capital B are the reactants, capital C and capital D are the product, whereas small a and small b are the stoichiometric coefficient for reactants, small c and small d are the stoichiometric coefficient for product. Okay, I hope you understood this reaction. Let us write the equilibrium constant for this particular reaction. So Kc is equal to concentration of product C raised to power small c, because small c is the stoichiometric coefficient, then concentration of product D raised to power small d, this we have represented here, divided by concentration of reactant A raised to power small a, because small a is stoichiometric coefficient of reactant A, into concentration of reactant B raised to power small b. Okay, this is the expression. Now same, if you want to represent in terms of concentration, same formula, then we have to write like this. What? Equilibrium constant in terms of concentration is equal to concentration of product C raised to power small c, stoichiometric coefficient. Similarly, concentration of product D raised to power small d, divided by concentration of reactant A raised to power small a into concentration of B raised to power b. So C here is concentration. Like this, we are going to represent Kc in terms of concentration. And same expression in terms of partial pressure, we have to write like this. How? Partial pressure of concentration of product C raised to power C, partial pressure of concentration product D raised to power D, divided by partial pressure of reactant A raised to power A and partial pressure of reactant B raised to power B. So this is the expression of Kp and Kc for this particular reaction. Remember this. Now let us move further. We know about ideal gas equation, PV is equal to nRT. We can rearrange this equation as PV is equal to nRT by V, and we know number of moles divided by volume is concentration. Okay, in place of N by V, we can substitute C. So we get one new equation, P is equal to CRT. After substituting C in place of N by V, we got P is equal to CRT. P is partial pressure, P is pressure, C is concentration, R is universal gas constant, and T is temperature. Now this formula we used to represent the partial pressure of products and reactants. So which are the products? C and D. Which are the reactants? A and B. So this formula we used to represent the concentration or partial pressure of product CD and reactant AB. Then we got these formulas. Partial pressure of reactant A is equal to concentration of reactant A RT to the power of small a. Small a is stoichiometric coefficient. Similarly for B, and product C and product D we have expressed this like this. Now, but in place of this formula for the expression of equilibrium in terms of partial pressure, we are going to substitute the above values. What values? In place of this, we are going to write this value. In place of this, we are going to write this value. Similarly, in place of A, partial pressure of reactant A, with this value. In place of partial pressure of reactant B, this value that we have written. Okay, we have substituted. Okay, where R and T are the constant. R universal gas constant and temperature T is constant. So here common, that only RT is common. So what we are going to do, we are going to separate out the constant RT. So we got this equation. By modifying this, we got this equation. Now let us simplify further. We know the value of this. We already done the expression of equilibrium constant in terms of concentration, this one. So in place of this, we can write Kc. Simple. Okay. So I have I can write Kp is equal to Kc. Kc from where? In place of this, I have written Kc. That's all. Okay. Then this I have written as such, RT to the power of C plus D divided by RT to the power of A plus B. Okay, that we have written in this equation. Now let us further simplify. Again we are going to take RT as a common. Then we get RT raised to power Kp is equal to Kc, RT raised to power C plus D minus A plus B. Please remember this. This is the formula. RT to the power of this one, C plus D minus A plus B. Now we must remember here A and B are the stoichiometric coefficient of reactants that represents number of moles. So in place of A plus B, we can write number of moles of reactant. And C plus D are the stoichiometric coefficient of products. So in place of C plus D, which means number of moles of product C and D, we can take number of moles of product NP. Okay, this you clarify. So in place of this CD minus A plus B, in place of CD I can take NP, number of moles of product. In place of A plus B I can take number of moles of reactant. So that shows was delta N, change in the number of moles. So finally we get the relationship of Kp and Kc is equal to Kc RT to the power of delta N. RT is constant, delta N is what? Change in the number of moles NP minus NR. I hope you understood this relationship. Let us look at to the entrance exam questions related to this expression Kp is equal to Kc RT to the power of delta N. So when the number of moles of reactant and product is same, here 2, number of moles of reactant also 2, number of moles of product also 2, then delta N value what we got? 0. So this, in this case, when delta N is 0 or when number of moles of reactant and number of moles of product are same, then we will get Kp is equal to Kc. If we find that number of moles of product is more than the number of moles of reactant, when the number of moles of product is more than the number of moles of reactant, then delta N value we will get +1. Then according to the previous expression, we will get Kp is greater than Kc. Very important. You must remember, in entrance exams they are going to ask this such type of questions. And if number of moles of reactant is more than the number of moles of product, then delta N value we will get -1. Then in that case Kc is greater than Kp. This relation you should remember. I hope you understood. Remaining part of this chapter we will I will come with a new video. Please revise this video properly and understand. If any doubt, please mention in the comment section.